In this video, we're going to talk about problems from 3.8. Marginal analysis is going to be the big topic here. The section is titled as differentials and marginal analysis. We're going to be talking about marginal analysis though. So let's look at number 13. And we're going to start off with a cost function of 0.05x squared plus 4x plus 10, and we're given a starting x value of 12, and we're told to use a delta x of 1 in this for our analysis. So what we're going to do is we're going to use the idea that for small values of delta x, that dc is approximately delta c, dp is approximately delta p, dr is approximately delta r. And we're going to find the error in this. And I'll talk about something at the end. There's another kind of analysis that we can do with the error. I'll mention that at the end. We don't do any of those error analysis problems, but we'll just be finding the raw difference between our estimate and our actual value here. So I have the calculator ready to help me find the actual value here at the end, and to find the estimated value if necessary. So let's start by finding the derivative. You're going to want to use the notation of dc dx. You're not going to want to call it c prime, because you need to see that dx and look at it kind of like it's a fraction that we're going to multiply by the denominator in a second. 2 times 5/100 is going to be 1/10 times x plus 4. So dc is exactly equal to 0.1x plus 4 dx, and dx is exactly the same as delta x, but when I make that substitution, dc is only approximately delta c, so I have to stick an approximately equal to symbol in here. 0.1x plus 4, and there we go. And we'll see why it's an approximation here. So delta c is approximately, and then 0.1 times our x value was 12 plus 4. We want to multiply by a delta x of 1 for this problem. So delta c is about 1.2 plus 4 times 1 is 5.2 times 1 will give me $5.20 for my approximation of delta c. Now delta c is exactly equal to c of 13 minus c of 12, which is going to be 0.05 times 13 squared plus 4 times 13 plus 10 minus 0.05 times 12 squared minus 4 times 12 minus 10. And I'm just going to show you this time all these steps, and then I'm going to kind of skip down to this second step moving forward. So I see the 0.05 is common, and that's 13 squared minus 12 squared. And I have plus 4 times 13 minus 12. and the constants will always zero each other out. So this is going to be 0.05 is 5 over 100 is 1 over 20. 13 squared is 169. 12 squared is 144. And this is going to be 25 over 20 plus 4. So this is 1 1/4 plus 4 is exactly 5 1/4. And so my difference here is 5 cents between my estimate and my exact value. Not bad. So it was a lot easier to calculate something that was first degree than something that was second degree, where I had to find the difference. So much easier calculation for DC than for delta C, which is why we use it for the approximation if we just need a good enough answer and not an exact answer. Let's go ahead and look at number 14. And it tells us that C is equal to 0.025x squared plus 8x plus 5. Our given x value is 10, and our delta x value is 1. dc dx is 0.05x plus 8. So dc is exactly 0.05x plus 8 times dx. So my delta c is about 0.05x plus 8 times delta x, where delta c will be approximately 0.05 times 10 plus 8 times 1 will be 0.50 plus 8.00 is 850. And then delta C is exactly equal to C of 11 minus C of 10 will be 0.025 times 11 squared minus 10 squared plus 8 times 11 minus 10. The constants will go away. So this is 1 over 40 times 121 minus 100 plus 8 times 1 is 21 over 40 plus 320 over 40 is 341 over 40. 341 over 40 is delta C is exactly equal to $8.50, we'll say approximately 53 cents, because we're going to have to round to the nearest cent. So our difference is 3 cents here. So now at number 15. Now we have R equals to 30x minus 0.15x squared. Our given x value is 75. Our delta x is 1 again. So dr dx is 30 minus 0.3x. dr is exactly 30 minus 0.3x dx. So delta r is 30 minus 0.3x delta x approximately. So delta r is approximately 30 minus 0.3 times 75 times 1. Delta r is approximately 30 minus 22.5 times 1 is going to be equal to $7.50. And delta r is exactly equal to r of 76 minus r of 75 will be equal to 30 times 76 minus 75 minus 0.15 times 76 squared minus 75 squared. I'm not doing that in my head. 30 times 1 minus 0.15 times 76 squared minus 75 squared is 151, and 30 minus 0.15 times 151 is going to give me 735, difference of 15 cents. Now number 16. Says r is equal to 50x minus 1.5x squared. So dr dx is 50 minus 3x. dr is exactly 50 minus 3x dx. So delta r is approximately 50 minus 3x delta x. And x was 15 in this problem with delta x equal to 1. So delta r is approximately 50 minus 3 times 15 times 1 is 50 minus 45 times 1 is 5 times 1 is $5. Then delta r is exactly equal to r of 16 minus r of 15 will be 50 times 16 minus 15 minus 1.5 times 16 squared minus 15 squared is 50 times 1 minus 1.5 times 256 minus 225. So this is equal to 50 minus, and I'll call that 3/2 for myself. And then the difference here is 31. 31. So this will be 100 minus 93 over 2 is 7 over 2 is $3.50. Difference of $1.50. 17 is a profit function, capital P, negative 0.5x cubed plus 2500x minus 6,000 with x equal to 50 and delta x is still equal to 1. dp dx is equal to negative 1.5 x squared plus 2500. dp is exactly equal to negative 1.5 x squared plus 2500 times dx. So delta p is approximately negative 1.5 x squared plus 2500 times delta x. So delta p is approximately negative 1.5 times 50 squared plus 2500 times 1 will be negative 1.5 times 2500 plus 1 times 2500. Just putting that 1 in to be explicit because of what I have to do next, where I factor out the 2500 and make this negative 1.5 plus 1. 2500 times a negative 0.5 or a negative 1/2. That makes delta P approximately negative 1, 2, 5, 0. I'll put 0.00. Delta P is exactly equal to P of 51 minus P of 50 will be negative 0.5 times 51 cubed minus 50 cubed plus 2500 times 51 minus 50. And let's go ahead and just put this in the calculator. Negative 0.5 times 51 raised to the third power minus 50 raised to the third power plus 2500 times 1 is plus 2500. So that's going to be delta P is exactly equal to a negative 132550 and 132550 minus 1250 is a difference of $75.50. Now at number 18. 18 gives us a profit function of negative 0.1x cubed plus 900x minus 50, an initial x value of 60, and a delta x that is equal to 1. dp dx is equal to negative 0.3x squared plus 900. So dp is exactly equal to negative 0.3x squared plus 900 times dx. So delta p is approximately negative 0.3x squared plus 900 times delta x. Delta p is approximately negative 0.3 times 60 squared plus 900 times 1. And we have delta p is approximately -3/10 times 60 times 60 will make 360 times 3 is -1080 plus 900 is a -$180. My delta P is exactly equal to P of 61 minus P of 60. It's equal to -0.1 times 61 cubed minus 60 cubed plus 900 times 61 minus 60. The constant will go away. -0.1 times 61 to the third minus 60 to the third is 10,981 plus 900 will be a -1098.10 plus 900 -1098.1 plus 900 is a -198.10. So the difference of $18.10. Let's go ahead and move on to number 33 now. Just later in the problem sets, we get some word problems that go over the same topic. So we're given a profit function, P, and it's not simplified for us yet. We have a revenue function here minus a cost function here. And we need to simplify that before we get started. But this is going to be -1 and -1/2 is -3/2 x squared. Then +77 and +500 is 577x minus 3000 will be our profit function. dp dx will be a -3x plus 577. So the x is going to be 115, and now our delta x is going to be 5. So dp will be exactly equal to -3x plus 577 dx, making delta p approximately -3x plus 577 times delta x. Delta p will be approximately -3 times 115 plus 577 times 5. So that will be -345 plus 577 times 5 will be 232 times 5 will be $1,160. My exact value of delta P will be P of 120, that's the 115 plus the 5, minus P of 115 is going to be -3/2 times 120 squared minus 115 squared plus 577 times 120 minus 115, and the constant part is going to go away. So delta P be exactly -3/2 times 120 squared minus 115 squared is 1175 plus 577 times 5, so -1.5 times 1175 is a -1762.50 plus 755 times 5. Sorry, 577 times 5 is 2885. 2885 minus 1762.5 is 1122.50. And that's a difference of $37.50. Look now at number 34. $34 gives us a revenue function of 900x minus 0.1x squared. Tells us we want to use marginal analysis to estimate delta R when initial X value is 3,000 units and delta X is equal to 100 units. That means going from 3,000 units to 3,100 units. So dr dx is 900 minus 0.2x. dr is exactly 900 minus 0.2x times dx, making delta R equal to 900 minus 0.2x delta x, and that's an approximation. So delta R is approximately 900 minus 0.2 times 3,000 times a delta x of 100. So delta R is approximately 900 minus 600 times 100 is 300 times 100 is 300,000. That's $30,000. And delta R is exactly equal to R of 3,100 minus R of 3,000. So that will be 900 times 3,100 minus 3,000 minus 0.1 times 3,100 squared minus 3,000 squared is 900 times 100 minus 0.1 times 3,100 squared minus 3,000 squared is 61,000,000. So when I take 1/10 of that, this is 9,000,000 minus 61,000,000. 9,000,000 minus 61,000,000 is 29,000 dollars exactly. So there's a difference of $1,000. At $35. Number 35 gives me a demand function P, lowercase p, is equal to 68 minus 0.2x. And it wants me to find the revenue function, which is xp. It's equal to 68x minus 0.2x squared. And then it wants me to use these marginals to estimate delta r when x is 7 and delta x is going to be 1. So dr dx is going to be 68 minus 0.4x. dr will be exactly 68 minus 0.4x dx. And delta r is approximately 68 minus 0.4x delta x. So delta r is approximately 68 minus 0.4 times 7 times 1. It's going to be delta r is approximately 68 minus 2. It's 2.8 times 1. 68 minus 2.8 is 65.20. Delta r is exactly r of 8 minus r of 7 is equal to 68 times 8 minus 7 minus 0.2 times 8 squared minus 7 squared. So delta r is exactly 68 times 1 minus 0.2 times 64 minus 49 is 68 minus 0.2 times 64 minus 49 is 15. So that is 68 minus 3 is 65.00. A difference of 20 cents. Part B asks us to repeat that second set of steps there for x is equal to 70 and delta x is equal to 70. I'm sorry, is equal to 1. So the change from 70 to 71. So that means that delta r is approximately 68 minus 0.4 times 70 will be 28, and times 1 will be $40, and r of 71 minus r of 70 will be exactly what delta r is here. So that will be 68 times 71 minus 70 minus 0.2 times 71 squared minus 70 squared. I'll be using my calculator for that for sure. So minus 0.2 times 71 squared minus 70 squared is 141. 141 times 0.2 is 68 minus 28.2 is 39.80. And so we have a difference here of 20 cents. And we had a difference up here of 20 cents. So don't think that those will always be the same. When you change the X values, they may not be. I'm going to skip number 36 for the sake of time because it's a picture that you look at in the book and it's a how you see it problem. There's not really any calculations there to do. No equations given, just a graph. So I'm going to move on to number 37, which is the next one that gives me an equation. And it has to do with the size of a herd of deer that they put, I think it was 50 deer into a particular area, and they found that this formula tells them what the size of the herd will be T years later, and they want to find the rate of change. They want to approximate the rate of change between years 5 and 6. So no, I'm sorry, 5. Yeah, 5 and 6. So there we go. So we're going to say dn, I'm going to write this as 50 plus 30t over 1 plus 0.04t. So dn dt is derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So simplifying the numerator, dn dt is equal to 30 plus 1.2t minus 2 minus 1.2t 1 plus 0.04t quantity squared. It's going to be 28 over 1 plus 0.04t quantity squared. So dn is exactly equal to 28 over 1 plus 0.04t quantity squared times dt, and delta n is approximately equal to 28 over 1 plus 0.04t quantity squared times delta t, which is delta n is about 28 over 1 plus 0.2 quantity squared times 1 is 28 over 1.2 quantity squared. 28 over 1.2 times 1.2 is about 19.44. And because we're dealing with deer here that have to be in whole numbers, we're going to say that that's going to be about 19. So the change in herd size will be approximately 19 deer that year that we're talking about between years 5 and 6. Let's move on and look at number 38. Says, see the concentration of a drug in the bloodstream measured in milligrams per milliliter is 3t over 27 plus t cubed. And we want to find the change in concentration between 1 hour and 1.5 hours after the drug is given. So delta t equals 0.5. dc dt will be derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. That will be 81 plus 3t cubed minus 9t cubed over the quantity 27 plus t cubed squared. dc dt will be equal to 81 minus 6t cubed over the quantity 27 plus t cubed raised to the second power. So dc will be exactly 81 minus 6t cubed in the numerator, 27 plus t cubed quantity squared in the denominator, times dt, making delta c approximately 81 minus 6t cubed over 27 plus t cubed quantity squared times delta t, where t was 1. So that's 81 minus 6 over 27 plus 1 raised to the second. And delta t was 1/2 or 0.5. So that's 81 minus 6 is 75. 28 squared. So 75 times 0.5 is 37.5. 28 squared is 784. 37.5 divided by 784 is delta C is approximately, and I'm going to call that 5/100ths of a milligram per milliliter per hour. And we were not told to compare that to the actual change in concentration, just to find the approximate change in concentration there. Let's look at number 39. We're given a couple points with demand and price that, if I remember right, these are watches being sold, that 150 watches are sold when the watches are sold at $50 a piece, and the quantity sold drops to 120 when the price is raised to $60. Assuming that it's a linear demand function, we have P minus 60 is equal to 120, 60 minus 50 over 120 minus 150 times x minus 120 is going to be P minus 60 is a 10 over negative 30, x minus 120, p minus 60 is equal to a negative 1/3 times x minus 120. P minus 60 is a negative 1/3 x plus 40. Add 60 to both sides. And I have that P is equal to 100 minus 1/3 x. Revenue is XP. So that's going to be 100x minus 1/3 x squared. And my dr dx, since I want to estimate delta r, is going to be 100 minus 2/3 x. dr will be exactly 100 minus 2/3 x times dx, and delta r will be approximately 100 minus 2/3 x times delta x. So we're given an x of 141 and a delta x of 1. That gives me delta r is approximately 100 minus 2/3 times 141 times 1. 3 goes into 141 47 times. So 100 minus 94 is $6 for my estimated delta R. And we're asked to kind of sketch a graph of this. That's really hard to sketch a graph. I'm going to have to put some things in the calculator here and zoom in for you. So my revenue function that I'm interested in is 100x minus x squared over 3. So there's that function. And then the next function that I'm interested in is going to be this tangent line. If I were to draw that, so there's my slope of my tangent line would be dr dx would be 6. So this is going to be y equals to 6x, and then if I had let's see, y minus, I want at 141. So what is r at 141? Oh, 141 of 141 is 7473. Minus 7473 is 6 times x minus 141. 473. This is my tangent line, is 6 times 141. Six, so 7473 minus 846 should give me y equals 6x plus 6628. There's my second equation that I want to put in here, 6x plus 6628. And I'm using this tangent line to the curve to approximate things that are going on close to this point of tangency. So I know that At they should be the same value here at 141. So where did I make my mistake? This was exactly 6 times x minus 141, and then let's try this again. 7473 minus 6 times 141 is 6628. That's right. Type it in right. 6x plus 6628. That's right. So these should be exactly the same thing. I don't know why they're off at all. But the tangent line should touch the curve exactly at the same y value. So that's just something with the calculator being funky there. But let's go ahead and look at 142 now. And we can see that r of 142 is exactly, let's say approximately 7478.67, and my estimated r of 142 is equal to 7480 for a difference of 7480 minus 7478 0.67. That really was 2/3. So it's a difference of 1 1/3. And my picture that I originally had, there was just a difference of 1/3, which comes back somehow to the fact that this was off by 1 here somehow. So I'm really not sure how it was. But anyways, the graph should look something like this. I am looking at my revenue function here. It should have an x-intercept at 0, and it should have an x-intercept at 300. Halfway in between there is going to be 150. We're somewhat close to that over here at 144. So there's my tangent line. I'm going to use my tangent line to help me approximate. So I'm going to zoom in just on this little bit of the curve right here. It's barely changing, but it's a little different than this. So here's 144 for me, and here's 145 for me. And at 144, we should have, I'm sorry, 141. Is that what's wrong? Did I put in the wrong numbers? No. At 141, they should coincide at 74, 73 exactly. And then here, the curve is going to be exactly 74, 78 2/3, and the approximation is 70 is 142. 142. This point is 142, 74, 80. And you can see the difference there is I got 79 here when I did it before. So the difference there is just a third of a dollar, or about 33 cents. So go back and check why the calculator is giving you different numbers than the textbook. Maybe the calculator is right. Maybe it's $1.33, but it's really close. That's what I want you to see, is that I have to zoom in a lot here to sketch this graph, and this tangent line stays really close to that curve. As I stay close, relatively close to 141, and 142 is close enough that I get a good approximation there. I have one more problem that I want to do with you here in this video, and it's very similar to the last one we just did. These are just webcams instead of watches. We're told that with number 40, we get 30,000 units are sold at a price of $25. And when we change the price to $20, we sell 40,000 units. So my P minus 20 is equal to change in Y over change in X. Times X minus that. So P minus 20 equals -5 over 10,000, X minus 40,000. So that's going to be P minus 20 is equal to -1 over 2,000 X, and then 10,000 goes into 40,000 4 times. -5 times -4 is a positive 20. Add 20 to both sides. We get that P is equal to 40 minus 1 over 2,000 X. So my revenue function is XP is 40X minus 1 over 2,000 X squared, making dr dx equal to 40 minus 1 over 1,000 X. dr is exactly 40 minus 1 over 1,000. Let's just call this 0.001 X dx. And delta R is approximately 40 minus 0.001 X delta X, meaning that delta R is approximately 40 minus 0.001 times, and then my X that was given to me in this problem was 28,000 units. My delta X that was given to me was 1, so 28,000 times 1 is going to be 40 minus 28 times 1 is going to be oh, hang on. I got ahead of myself. I only got my revenue function. I was also given a cost function. Just give me a second. I was told that the investment cost up front was $275,000 upfront cost, plus I have a cost of $17 a unit. So my profit function is my R minus my C is 40x minus 1 over 2,000 x squared minus 275,000 minus 17x. So my profit function, 40 minus 17 is 23. X minus 1 over 2,000 x squared minus 275,000. All right, now we're ready to take the derivative to find marginal profit. dp dx is 23 minus 1 over 1,000x. dp is 23 minus 0.001x times dx. Delta p is approximately 23 minus 0.001x delta x, and now we're told that x is 28,000 and delta x is 1. So delta p is approximately 23 minus 28 times 1 is a -5 times 1, that's a -$5 of lost profit by increasing to another unit. We should not have done that. So now we want to sketch this graph, and again, that would take quite a bit of time. I just kind of did that previously with the other problem, but let's look at the profit function here. Is going to be 23x minus 1 over 2,000 x squared minus 275,000. And we have our tangent line here that y will be equal to -5 times, and this is going to be x minus, and this was 28,000. So 28,000. We have plus 23,000 over here. So this is y plus 23,000 equals -5x plus 5 times 28,000 is 140,000. 140,000 minus 23,000 is 117,000. Okay, so that's my tangent line, and then I can say, all right, we have a profit curve, which is let's just let the calculator draw this for me. -5x plus 117,000, and I want to be close to 28,000. So let's go 27,500 to 28,500 by increments of 100. My y value is needing to be close to 23,000. So let's go between 20,000 and 25,000 by increments of 1,000 here, graph. Uh-oh. Zoom 0. All right, here we go. So so if we trace here, there's 28,000, and then 23,000 is that point. And now if I trace and go to 28,001, you can see that, let me just do that in the table here, 28,001. We have P of 28,001 is a negative 23005.00, and estimated P of 28001 is negative 2300500, a difference of nothing. That's really good, right? Really, there's a difference of 0.05 of a cent, but that's undetectable. So because we're so close to our point of tangency here relatively, then our tangent line gives us a really good approximation of what's going on with the curve, and it's much easier to find the y value of the tangent line than it is to find the y value of the curve. So another name for this that you might see other places is called linearization. And you use the tangent line to linearize the graph at that point, but you get this little bit of error. So you have this curve here, like we were saying, and I'm going to try and exaggerate it a little bit, that we have the exact y value and we have the approximated y value, and there's a little bit of a difference there between the tangent line value and the actual y value of the curve. The further that we get away from this point of tangency here, the more error there's going to be between the graph and the tangent line, and the tangent line at this point doesn't become a good estimate anymore. We would have to move closer to this point that we're interested in to get a good estimate. So we're also interested not just in absolute error like we've been talking about, but also something called relative error or percent error. You do that a lot more in science classes to say that your relative error would be, for instance, your dp divided by your p, your estimated value divided by your actual value. And then if you want to change that to a percent error, you would take your relative error and multiply it times 100%. So estimated over actual gives you relative error. As a decimal, change that to a percentage to say what your percent error was, and you can kind of figure out, was that a good estimate or not by what your percent error was. All right, that's it for this section. And all we have left in this chapter is to go over some chapter review problems, and then we'll be done with our discussion of chapter 3. So we'll come back and do those review exercises next time. See you for the next video.